We'll start now. Question 1. Assign EZ config designation for each of the following compounds. The first compound that we have there, I'm gonna just draw it again. We have got a pH, okay? But instead of me drawing that pH, what I'm gonna do is I'm going to write the structure for that group. It's like that, and then it is with alternating double bonds, okay? And then you have got the double bond with oxygen, and then down you have got a cyclohexane, and then on top you have a double bond nitrogen, hydrogen, and then down you have got an OH. So the way you determine the RS configuration, I mean the EZ configuration of this compound, okay, is you are going to look at the priority of the groups that you are talking about. So for the first one, that pH is known as a phenyl group. It's basically when a benzene acts as a group, that's known as a phenyl. And then, so a phenyl group has got how many carbons? It has got 6 carbons, and then it's going to have 5 hydrogens. Okay, and then the group that is down, that is a cyclohexane. So now you are comparing between a phenyl group and a cyclohexane. Which one is going to be able to have higher priority? So basically, count the number of carbon atoms and then the number of hydrogens. That is what is going to determine which compound has got a higher priority. So in this case, for this one, the more the double bonds you have, the fewer the hydrogens that you are going to have. Okay, and then, so meaning that between the group that's on top and the group that is down, the group that is down actually has got a lot of hydrogens than the group that is on top. Okay, so meaning that the group that is going to be down is going to have higher priority, because remember, just here you have got 2 hydrogens, but for this one on top you only have 1 hydrogen on top, and that makes it different. Okay, I hope that makes sense. And then the next one, you look at this, you have got a nitrogen, and then you have got an oxygen. Again, look at which one is going to have higher priority. You have got the amine, so because you have got actually a carbon here, and that carbon, there is a nitrogen attached. And then you also have a carbon here, that carbon, there is an oxygen that is attached. So which one is going to win in that case? Okay, so oxygen is in group 6, right? I mean, yeah, in group 6, it has got an atomic mass of 8, nitrogen has got 7. So oxygen is going to have higher priority because this is a carbon, this is a carbon, none of them can actually win. So you go to the next atoms, so which is a nitrogen and oxygen. So in this case, the oxygen is going to win. So this is going to carry 1. Okay, so then looking at the higher priority groups are on the same side. What configuration is that going to be? You can see both of them are actually down. So this is the Z configuration. Okay, if it is E, those are going to be on opposite sides. And then for the second question, I hope that makes sense. For the second question, you can see the way it is. Again, you have got a phenyl, which is the same way, like that, alternating double bonds. Then you are going to have a double bond down. You have got a sulfur attached to an hydrogen, and then you have got a double bond with oxygen, and then you have got an OH, and then down Okay, I've got something like this. So again, look at the masses. On top you have got a phenyl, down you have got this guy with 5 carbons. So a phenyl has got 6 carbons, so it's going to have higher priority, so that will be 1. And then over the other side, you are having, first you are going to compare, this is a carbon, this is a carbon, so none wins. And then go and look at the next atoms they're attached to. So this is a sulfur, and then the other one, this is an oxygen, right? So I've got a sulfur and an oxygen. So which one is going to end up winning now in that case? So the one that will end up winning, try again to find the molar mass. The molar mass of sulfur, checking on the periodic table, that is a 32. Okay, so that's a 32. And then oxygen, the molar mass is what? 16. So on this carbon, this is the same molar mass. That's carbon. That's 12. Even this one is 12. The next atom, this is 32. And this is oxygen, another oxygen. That's another 32. And of course, we have got hydrogen here, then hydrogen here. So that's the same molar mass. But this carbon here actually has got 2 hydrogens that is attached to. So what am I saying? At the end of it all, the group with sulfur is going to have higher molar mass, because here the carbon and the carbon have got the same molar mass. Oxygen is 16 plus 16, that's a 32. And the sulfur also is 32. So those cancel out. There is this hydrogen, it has got a molar mass of 1. Even this one has got a molar mass of 1. That cancels out. But the carbon at the beginning, the first one has got a molar mass of 1. Even the other one, the molar mass is also 1. So that means, oh, this carbon on top has got 2 hydrogens. 1 plus 1, that will be a 2. But the carbon that is down will not have any hydrogen, because it's already bonded to 4 different things. Okay, so meaning that the group of priority here is going to be still the one on top. This is still a Z configuration. So both of them are Zs. So how do you determine Z configuration? Z, you look at groups of high priority on same side. Okay, and then when you're looking at the E configuration, the groups of high priority are on opposite sides. And that's very important to make sure that you just understand. The next question, chloramphenicol is a broad spectrum antibiotic that is particularly useful against typhoid fever. What is the configuration of its asymmetric center? The configuration of the asymmetric centers. So the first thing is you need to know which ones are the asymmetric centers. So for the asymmetric centers, you have got this one here, okay, that carbon, and then you have got also this carbon. Let me start with the first carbon. This carbon is actually attached down to a nitrogen, and then it is also attached to a carbon that is attached to an OH, and then it is attached to another carbon, which on top is actually attached to an oxygen and hydrogen. And of course, there is a group this side, and then it continues like that. One thing that you can see here is the hydrogen on this carbon. So if the hydrogen is not shown, it means that's actually in front, because the nitrogen is at the back, so the hydrogen is in front. So I need to number the carbon atoms. I mean, you need to number the groups which have got priority. The atoms directly attached to the carbon. So you have got nitrogen, that will be number 1. Okay, because the next atoms attached, I've got a carbon here and then a carbon here. Nitrogen has got higher molar mass than carbons. So those are the ones that will win. For the other two carbons, you can see that this is a carbon, this is a carbon, so none of them will win. Look at the next atom where they are attached. This one is attached to oxygen, this one is also attached to oxygen, so none of them will win. But when you look at this carbon, it's also attached to another carbon this side. But for this carbon, it's not attached to any other carbon. It's only attached to hydrogens. So this group will end up winning. And this will be the third. Now count from 1 to 2 to 3. Okay, that's supposed to be the configuration. But now because this molecule, the fourth group, which is the hydrogen, is actually at the back. So swap configuration. This was supposed to be S, so this was going to be R configuration. Okay. And then for the other carbon here, you have got a carbon. On top, there is an OH. And then this side, there is a ring. Carbon. Okay, there is that ring. And then there is also another group this side. Okay. Again, the hydrogen you can't see is actually in front. So again, the group of highest priority or the atom of high priority directly attached to the carbon, you have first oxygen. The next you have got carbon, this carbon, and then this carbon. So none of them wins. So look at the atoms they are now attached to. This carbon is attached to a nitrogen, but this carbon is attached to another carbon. And nitrogen has got high priority. So this will be number 2. And then this will be number 3. And then again also count from 1 to 2 to 3. Supposed to go like that. But of course, the fourth group is in the front instead of at the back. So it's supposed to be S configuration. So swap the configuration. This is also going to be R. So both carbons have got R configurations. Hope that's okay. So this is supposed to be S, but swap. Cause fourth group is not at the back. How do you know the back? You look at the wedges. The next question says, rank the species in each group in order of increasing living group ability. Now, how do you know which living group is going to be a better living group? So for the living group ability, you look at the stability of the living group. Living group ability, living group ability is determined by the stability of the living group. Okay. And by stability, what do we mean? So those living groups that are going to be weaker bases are actually better. Okay. Number 1, weaker bases. Besides weaker bases, those that are non-charged molecules are more stable. So this is what you need to know. So when you look at the first question for I, you have got OH, fluorine, and nitrogen. You are comparing atoms that are in the same group in the periodic table. Actually, they are in the same period, that is period 2. So you have got oxygen on the periodic table. Okay, basically what we are doing is we are going on the periodic table. Oxygen is in period in group 6, nitrogen in group 7, nitrogen group 4. Okay, nitrogen is actually going to be before oxygen. So nitrogen is in group 5, oxygen is in group 6, and then fluorine is in group 7. Okay, and as you go in this direction, the electronegativity is actually increasing. Now, by definition, electronegativity is basically the tendency of an atom to pull a pair of shared electrons towards its nucleus in a bond. So meaning that fluorine tends to pull electrons more towards itself in comparison to nitrogen. Okay. When you look at these guys here, when they form acids, okay, which one is going to be the strongest acid? That should be the question. So the strongest acid in this case is going to be the strongest acid is going to be HF. This guy with a fluorine. And the reason for that is so when hydrogen is attached, this is going to be the strongest, okay, in comparison to oxygen and in comparison to the others. Okay. So that's the strongest acid, HF. Now the strongest acid is actually going to form the weakest conjugate base. Why? Electronegativity. The reason as to why this one is very strong acid is because when it loses that hydrogen, it's going to form something that is negatively charged. And the more electronegative you are, the more likely you are to accommodate that negative charge. For example, if you've been experiencing a lot of pressure in your life, for example, you don't have a support system, more likely the pressures of this life you can withstand them than someone who can easily make a phone call, they send them money. The moment when their parents are no longer there, they'll struggle a lot. Okay. So if you are used to negative environment, if negative situations come, you easily withstand them than someone who is not used. So fluorine is more electronegative. It accommodates a negative charge more. So even if it loses that hydrogen to form a negative charge, it actually is more stable. So fluorine is the most stable base. Okay. So rank in order of increasing leaving group ability. So in this case, because the acidity increases as you go in this direction, so hydrogen fluoride will be the strongest acid. So it's gonna form the weakest base. And weakest bases are the best leaving groups. Hope you get that. Okay. So the N is going to be the weakest when it comes to leaving group. So NH2 should be the weakest, and then followed by, oh, this, if I use that arrow means it's greater. We're writing in increasing. Okay, followed by OH minus, and then followed by F minus. Okay, so that is that. And just for you to know the reason, F minus is the weakest base because it comes from the strongest acid. Please feel free to ask in case you have got a question. Because of that, it is more stable as a living group. Okay, for number 2, you are comparing the guys that are in group 7 of the periodic table. So in group 7, when you look at the periodic table in group 7, you have got fluorine on top, you have got chlorine, you have got bromide, you are going to have iodine. As you go down, the atoms are becoming bigger. Okay, so the bigger you are, so they will be like this. This guy is very big. This is just a bit. This is just a bit. So it is like that. So if fluorine is attached to an hydrogen, it means that that hydrogen is very, very close to the nucleus of fluorine. Chlorine is attached to hydrogen, it's at least. If this one is attached, so the distance is increasing. Like in iodine, the distance of hydrogen to the nucleus of iodine is actually very big. So the way you are at school right now, you can easily be lost because you are away from your parents. So same, this hydrogen is more away from the nucleus of iodine, so it can easily be lost. And the easier it is to lose an hydrogen, the stronger that acid is. So hydrogen iodide is the strongest acid in the group. And then hydrofluoric acid is the weakest acid. Why? Because the hydrogen is so close, so it is very hard to lose it. Just like the way you and your partner are. It is very hard for you to let go of your partner because you are very close. Okay? So it is very hard for you to let go of your partner because you are very close. But if you are very far away, you can easily let go of your partner. And so if you can easily let go of your partner, it means that you're a strong person. Okay? But the ones that can't easily let go, they are weak. Once they just let go, they start crying. No, they've broken my heart. Because you were too close, so even the immediately you lost them, you started crying because you weren't expecting that. So you were a weak acid. So meaning that in this case, when you're forming bases, the strongest base is going to be this guy on top. I hope you are getting the explanations. Okay. So which one is going to be the strongest base? So with the strength of bases is going to also be as you go up. Okay, very important. So Hi is the strongest acid. Oh, by the way, yeah, this is the strongest acid, so to form the weakest base. Okay, so I minus is the weakest base, so it's the best leaving group, followed by Br, followed by iodine. Oh, sorry, followed by the chlorine. So chlorine is going to be the worst. Okay, so Cl minus, and then Br minus, and then I minus. Please, you need to know the explanations. So what's the explanation? I minus is weakest base because it forms strongest acid. And what's the reason? It's because of the size. So this one has to do with size. The one on top had to do with the electronegativity. And then for number C, yes, Jacob. Yes, polarizability on size, you also apply the principle of polarizability. Mhm. So the next one we are comparing again water, NH2, and OH. But when you look at these guys, NH2, nitrogen is in a group 5, oxygen is in group 6. Okay, you see? So you can compare these two guys. You can compare them. When you compare them, it is the same explanation that I gave earlier. So which one is more stable? Or which one is a much stronger acid? By the way, this compound is supposed to have a negative charge because you can't have any H2 having no charge. It's supposed to have a negative charge. Okay? Just like this one. So, meaning that we are going to compare the NH2 minus with the OH minus. And we already say that the NH2 minus is less stable than the OH minus. Okay, it's less stable than the OH. So meaning that the OH is more stable than NH2. But how about water? I said that non-charged compounds are very, very stable in comparison to those that are charged. So that means that water, the one which is actually charged, is going to be more stable than the OH. So for this one, NH2 is going to be the least stable, followed by the OH minus, and then water is going to be the most stable. Okay, so the reason is very simple. Uncharged compounds are better living groups. Hope that makes sense. Are we okay so far? Great. The next question, consider the following pairs of molecules. Identify the relationship between the two pairs given below as enantiomers, that's stereomers, constituent isomers, or the same compound. Show your reasoning. When you look at the first one, you have got two compounds that have got both of them have got 5 carbons. Okay, but then the only difference is in the connectivities. So different connectivities. What do you think those are? Or same molecular formula, but different structural formulas. What do you think those molecules are? Anyone? Same molecular formula, but different structural formula. It's the simplest. Is that thing you've been learning from high school that these are isomers. What do you call them? Those are structural isomers. Okay, because they basically have the same formula but different structures or different connectivities. So those are structural isomers. Structural isomers are known as constitutional isomers. Constitutional isomers. Okay, what's the reasoning? Same molecular formula but different connectivities. Connectivities, or basically different structures. So that's the explanation. The next question, you see the two groups that you are looking at. If you want to tell what kind of structure you have, look at each carbon atom and look at the atoms which are there. So this carbon, you have got CH3, chlorine, and NH2. This carbon, CH3, chlorine, and NH2. So that's the same. This carbon down, I've got OH, H, and CH3. This carbon, OH, H, and CH3. Okay. So meaning that you have got the same atoms. Now isomers can either be constitutional isomers or stereoisomers. So meaning that these two are going to be stereoisomers. But what type of stereoisomers? Because for stereoisomers, we can actually have enantiomers, diastereomers, meso compounds, cis and trans isomers, EZ configurations, such things. Okay, the cis and trans, those are the conformations. So we need to determine the RS configuration about each carbon atom. For the first carbon atom, the first group, this is going to be number 1, the one that's on top, because oxygen carries the priority. And then we have got a carbon here. This is also a carbon. But which carbon is going to win? The carbon here is going to win because it's attached to other bigger groups. So this will be number 2. And then number 3 will be this one. So count from 1 to 2 to 3. So from 1 to 2 to 3 is going to go like this. And the fourth group you can see, which is hydrogen, is already at the back. So this is going to be the error configuration. And then look at the next atom. So the first group here, I've got chlorine and nitrogen. So between chlorine and nitrogen, the question is which one carries the priority between chlorine and nitrogen? Anyone who think who has got who has a thought? Chlorine and nitrogen, which one will carry priority? So it's basically a chlorine because that's a higher molar mass. Okay, it's a chlorine. So this is going to be number one. Nitrogen will be number two. And then number three would be this big group this side. Let me circle this one so that you see that it's for the other one. So count again from 1 to 2 to 3. So it's like this. So the configuration here is still R. Okay, so this is R configuration. When we go to the next compound, the first carbon, this one, group 1 is this is a 1 chlorine, 2 will be nitrogen, 3 will be this big group down. So again, count from 1 to 2 to 3. Because the CH3 on top is actually not big. So this is going to be this, like this. But you can see the fourth group is at the back. What you need to know about Fisher projections is that what has been drawn here, I've got a carbon down. The group that is on top is actually at the back. And then the groups which are on the sides are actually in front. Okay, same way with this one here. That's what you need to know. The one that is down is also actually at the back. That is a CH3. So the carbon that is down, group 1 will be this one, group 2 will be this one, group 3 will be this one. Count from 1 to 2 to 3 is supposed to be like this. But you can see the fourth group is a nitrogen, but the fourth group is actually in the front. This was supposed to be S configuration, but because the fourth group is in front, this is going to be an R configuration. This is going to be R. The one on top, the fourth group was already at the back. So that is also R. So the first compound is RR. Second compound is also RR. Let me just double confirm that to just make sure that this is correct. Okay. So one, let me see the way I've circled them on this second carbon. This is 1, this is 2, this is 3. Oh, it was supposed to go like this, yeah? Supposed to be S configuration. But we are saying the fourth group is not at the back, so we swap. This is going to be R. The one on top, that is 1, 2, and 3. Okay. That's also R. Okay. So, meaning that for this group, for this second compound, you can see both of them have got the same configurations really. So those ones, that's the same compound. It's the same compound. What it's just been written in different structures or in different forms. The first one is in what we call a Sohos projection. The second one is in a Newman projection. Okay, they have got the same molecular formula, also same uh, structures, and also same configuration. So make sure that you know that. I hope that's okay. Please, in case you have got a question, feel free to ask. Is that okay? We can move on. So if let's say the first compound was ARA, And then let's say the second one was RS. If they differed at one position like this, the first carbon is the same, but the second carbon is different, we could have said these are diastereomers. Or if let's say the first one was RR, the second one is SS, or the first one was RS, the second one is SR. Both carbons have been swapped. We call these as enantiomers. All right. So that is how you go about that one. So let me just write what I've said. If this is R, this is R, this is S, this is S, let's say this is RS, this is SR, going in these directions, you're only changing one carbon. RR is now SR. You've just swapped the first carbon. RR is now RS. You've just swapped the second carbon. RS is now SS. You've just swapped the first carbon. So we call these as a diastereomers. And then this was RR is now SS. This was SR is now RS. We call these as a enantiomers. If any carbon has got a swap of configuration. The next question says, a 1.25 gram sample of cocaine with a specific rotation of negative 16 degrees was dissolved in 8.5 mL of chloroform and placed in a sample tube having a path length of 5 meters. What is the observed rotation? Is cocaine levorotatory or dextrorotatory? So this is a test that you want to use if you want to tell if a compound is optically active or not. So we're going to use a source of light. Let me just write a gamma candle like this as a source of light. And then you have got a tube. Okay, you have got a tube like that. And then there's a small opening here. So this tube has got a length L. Okay. And then of course inside you have got a solution which has got a concentration. The concentration you want it to be in grams per mil. The concentration of the compound that is there. The length, you want it to be in decimeters. So by the time, so these rays of light are actually going to be moving in all directions. But only the rays that are going in this direction will actually pass through this tube. When they pass through this tube, depending with the solution that is present inside, it will start rotating that light. To discover that by the time the light is reaching here, it would have rotated, is pointing at a certain angle. So depending with that angle, let's say this is 0 degrees, and say top is positive 90, and then down is negative 90, and then this is 180. So depending with where it's pointing, that will give us the angle. That is the rotation. That's the observed rotation. We give it alpha. That's the rotation, the angle. But of course, for different compounds, they have got a specific rotation. That is the rotation that we expect that compound to have. It is if it is pure. Because if a compound is not pure, the rotation that you are going to have is going to be, that is expected rotation, is going to be different from the observed rotation. Okay? So the first thing that you want to do is you need to calculate the concentration of the solution. And remember I've said that concentration is basically mass over volume, and the mass should be in grams. So the mass is, you've gotten a 1.25 gram sample of cocaine and you've dissolved it in 8.50 mils of chloroform. So that is 8.50 mils. And this is going to give you 0.147 grams per mil. The next thing that you want to do is, what is the length of the tube? The length of the tube, we've already been given that is 5 centimeters. But make sure that this is in decimeters. Okay? So you multiply. So what in 1 decimeter you have got 10 centimeters. So I've got a centimeter down and then a decimeter on top. So 1 decimeter, 10 centimeters. So this will cancel with that. This is going to give us 0.5 decimeters. Okay. And then the next, now you use the equation for the observed rotation. The question is asking for A, what is the observed rotation? So what you need to know is that the specific rotation is actually observed rotation over length times concentration. So the observed rotation observed is actually specific. So specific rotation, you write in brackets like this, and then times length times concentration. So the specific rotation, we are given the specific rotation is negative 16. Multiply that by the length, which is 0.5. Multiply by the concentration, which is 0.147. So if you multiply these values, you should be able to get negative 1.176. This is in degrees. Okay. The next question is cocaine level rotatory or dextrorotatory. So for substances that tend plain polarized light, to the right are dextro, and then to the left it is level. So that's the L and the D forms. So this is negative. It is turning left light to the left. So this is a level rotatory. Does this make sense? Is this okay? Okay. The next question, provide the mechanistic explanation to account for the following observation. Pseudolysis of 1-bromo-2-methylcyclohexane in methanol gives a mixture of 5 products. Okay, this is a pseudolysis. Basically, what is happening in this reaction is that you get the compound, and then of course, you are reacting it in water. Okay, it's reacting in water. What is going to happen is that this is by reflux. So what is going to happen is that the compound, the first step is that in this reaction, okay, the very first step of the process is you are going to lose the leaving group. This is going to go by a one mechanism when you're reacting in a methanol, this compound. So if I want to write it in steps, I'm going to say step 1, you have got this compound, you have got a BR, and then you have got that CH. So in the first step, what happens that the leaving group is going to leave. So what you are going to have is this compound. So there's going to be a positive charge here, and of course the BR has taken those 2 electrons and is negatively charged. Okay. In step 2, what happens is that there is a possibility of what we call a anhydride shift. There's going to be an anhydride shift, and hydrogen will basically move from where it is. Okay, so I'm going to write hydride shift. So remember there's a positive charge here. This is a secondary carbocation because the carbon containing the positive charge is bonded to other carbons. What happens that an hydrogen that's here, because this carbon contains only 3 groups, you can see, meaning that the fourth one is an hydrogen. That hydrogen will leave and come and attach here. And once it leaves, what you are going to see is that now where the hydrogen has left, there is a deficient of an hydrogen. So the positive charge will now go there. So this is a tertiary carbocation. And this tertiary carbocation is actually way more very, very stable. Okay, very, very stable. What is going to happen in the next step, that will be step 3. Any one of these guys that you can see here will now react with our alcohol, our methanol. Okay. The secondary carbocation and the tertiary carbocation can both react. That will be in step 3. So I'm going to write that. So let me start with the secondary one. There's a positive charge. So the methanol, I can write oxygen like this. Is bonded to CH3. It's also bonded to an hydrogen. This oxygen has got two lone pairs of electrons which will act as nucleophiles. So it's gonna go and attach on this carbon. This mechanism is actually SN1. And what you are going to form, you are going to have this. And then at this point, oxygen has attached. Then you have got CH3 and an hydrogen. This oxygen has got one lone pair of electrons because it actually had two. Now, when oxygen has got three things around it with a lone pair of electrons, it carries a positive charge. So what is going to happen at this particular point is the Br that left, which is the base in this case, can actually come and grab this hydrogen. Okay? It can come and grab that hydrogen. Once it grabs that hydrogen, you are now going to have a compound that is not charged. So very important, please take note that the hydrogen has to be grabbed. And whatsoever that is going to grab will basically be any what? Any base that is present in solution. Yeah. It grabs that. This bond breaks. So the product you are going to end up having will be this. So you have got now an oxygen attached to CH3. So this is one product. Of the products that you've been given, that is product number A. So this is A. You can see that's the one. And then, so this was coming from a secondary carbocation. Now, but from the tertiary. So from the tertiary, because this wouldn't have just used the secondary. This secondary product is actually not even very, very stable. Okay, it's not even very, very stable. Why? Because it's coming from a secondary carbocation. The very stable compound actually comes from a tertiary carbocation. So this product A is a minor product by SN1. The major product by SN1 is going to come from the tertiary carbocation. The same guy oxygen attached to CH3 attached to an hydrogen is now going to be the one going to attack this carbon. This is the SN1, and that is gonna form again oxygen there with CH3 and hydrogen. This is positively charged. So the Br or any base in solution can actually come and grab this bond breaks. Make sure you are writing the arrows correctly. Write full arrows, not half arrows. It is different to if I write an arrow like this and when I write an arrow like that. Use full arrows. Okay. So we are going to end up now oxygen here with CH3. That will be the next product, and that's actually the major product, and that's B. And then using again another thing that could have happened, let me write that as a step 4. These reactions, instead of them going by SN1, they could have gone by E1. That is an elimination reaction. Okay? Because when you're actually heating these compounds, that's the reflux. It can go by elimination. So I've got this compound with a positive charge here. And then what you see is that the same O, CH3 with an hydrogen, what happens is that you are going to look at one carbon away from where the positive charge is. Please take note, one carbon away. So you have got a carbon here, and then you have got a carbon here. So depending with which one has been grabbed. So if this carbon is grabbed, this bond will break, it will come near where the positive charge is. That is one possible product. And so what we are going to see is this. Okay, like that. Then you have got a double bond here. Now what could have happened again is that this could have actually come and grabbed this hydrogen, and then this bond would have broken like this. So another possible product we could have formed is this. Double bond could have formed here. These are not the only products. What you actually find out is that the other one, this is a secondary carbocation. The tertiary carbocation could have also done the same. Remember the positive charge here. And then also, just move one carbon away from the carbon that contains the positive charge. So for that one, again, you have got an hydrogen on top here or even here. But if you come and grab this hydrogen, the product you form is basically this same one here because this bond will break and go there. So we'll forget about that hydrogen because the product is going to be the same. But when you come and grab this hydrogen, what happens is that this bond can actually break and then it will form there a double bond. So another possible product would have formed is that we could have had a double bond here, okay, like this. So these are the possible products. There are 5 possible products. So this is actually the one given as D, and then this is C. The one that they've not shown here is this other product which is on top, but it's another possible product, but they've not just shown it. So this is a detailed mechanism of how you expect each product to come about. Any question on the detailed mechanism? Okay, we are going to end on this question for today. Mechanistically account for the formation of the following products in the reaction given below. How do you form these guys? So in step 1, when you want to form alcohols, you can actually just get alkenes and react them with acid, sulfuric acid. You end up forming alcohols. Okay? And in this reaction, the first step, what happens is that you have got your alkene. What the alkene is gonna do is that it's gonna grab an hydrogen from the acid. So I can write sulfuric acid like this: HOSO with a 3 and then hydrogen, so that it's just easy for me to grab that hydrogen. So what happens is that this hydrogen is gonna be grabbed, this bond is gonna break. There are 2 possible products that you form here, but of course one of them is going to be the major. It's either this hydrogen that is grabbed attaches on the end, on the carbon at the end, or it can attach on this carbon here. Okay, so what you are going to see is going to be this. So if the hydrogen has attached on the carbon on the end, means that this carbon that is here is going to be deficient of electrons, so it's going to have a positive charge. But If the hydrogen attaches on the carbon on the middle, it means that the carbon that is going to be deficient of electrons is actually the one on the end. This is the one that will be carrying a positive charge. Now this one is going to be the major product, and then the one that is down is going to be minor. What's the reason? This is a secondary carbocation, it's more stable than a primary carbocation, which is less stable. But of course, any one of them can form reactions. So in the next step, we'll go with the major product. Okay, so get the major product, which is like that. There's a positive charge here. What happens is that a shift is going to happen, but in this case, it's not an hydride shift like the previous question. This is going to be a methyl shift. Methyl shift. And the reason as to why shifts happen is just to attain stability. You can see that this carbon has got two methyl groups. It doesn't have any hydrogen at all because actually this carbon is attached to four different groups. So there's going to be a shift in hydrogen. So a shift in methyl. Okay. So this methyl is going to go there. And what is going to happen is now you have got like this. A methyl has gone here. So the positive charge that you can see has now shifted where the methyl was. That's where it has gone. Please don't forget arrows. Okay, very important. Now that you have formed this, in the next step, okay, these two possible products, we have got this secondary carbocation and this tertiary carbocation. They can either go by elimination reaction or by substitution. But this one more likely is going to go by by substitution because this is known as acid catalyzed addition of water. You also have the acid catalyzed dehydration of alcohols, which forms alkenes. It's like the backward reaction. This is a forward reaction. So what will happen now? The water that you can see here is now going to come in the next steps. Okay, so that is gonna be step 3. So starting with a secondary carbocation, which is like this, the positive charge here, the water, I'm going to write it like this, is now going to come in. This oxygen is going to go and attach on the positive charge. What you are going to see is something like this. So the oxygen having two hydrogens, that is of course the water is attached. Now this is going to be positively charged. At this point, what is going to happen is that, can you see that in step 1, we grabbed the nitrogen from the OSO3. So actually, there was another byproduct here. It was the OSO3H. This would have carried a minus because it's a byproduct. We have grabbed an hydrogen. That same byproduct, OSO3H minus, is going to come and now grab this hydrogen, breaking the bond. So what you are going to see now is going to be a compound like this. And so now you have oxygen just bonded to one hydrogen. This is one product. This is when we are using a tertiary carbocation. Another product would have come from when you are using this is from a secondary carbocation. The other one is going to be from the tertiary where I've got a positive charge here. So what will happen is that the OH2 here is going to now go and bind here on the oxygen, and that is going to produce the oxygen there, which has got two hydrogens, and then there is a positive charge there. Again, the same OSO3H is going to come in, going to grab the hydrogen, thereby breaking this bond, and this is going to form this product like this, where now you have got OH attached. So this is another possible product. And those are the two products that you can see. There is this one and there is this one. That is a mechanistic explanation for the two end products. Okay. Do we understand?